Welcome to today's lecture on gasometric assays. This technique is an essential part of analytical chemistry where we measure the volume of gas either released or absorbed during a chemical reaction. Now, imagine you are collecting gas in a balloon during a reaction. Gasometric assays help us measure exactly how much gas is in that balloon. This method is particularly important because it allows us to quantify specific compounds in mixture, such as how much carbon dioxide or oxygen is present. This method used in chemistry, as I said earlier, it's used to measure the volume of gas that is either liberated, that is released, or absorbed. Now, using a simple analog, like how we might measure the volume, the amount of water poured into or out of a container, but in this case, it's gas. This technique is crucial in analytical chemistry because it allows us to quantify certain compounds in a mixture based on the gas they produce or consume. To perform gasometric assays, we need a specific set of tools. The primary apparatus used in a gas is a gas burette, also known as nitrometer. Think of it as a specialized measuring cylinder that's designed to accurately measure gases. It has stopcocks to control the flow of gas and is connected to a balancing tube, which ensures that we can measure the gas volume under controlled conditions. This setup is critical for obtaining accurate and reliable measurements. It depends upon two types of operational concepts. One is either the measurement of the volume of the gas liberated under the conditions that are described in the assays. Two is to decrease in volume, to measure the decrease in the volume of gas when a suitable reagent is used to remove one of the gases present. This is the gas burette that is used. Now, the gas burette is provided with 2 or 3 stopcocks and the two-way outlet properly connected with a balancing tube. The balancing tube is also known as the leveling tube. It is carried out by the use of Hampfel apparatus. Now, the Hampfel apparatus is composed of burette and absorption pipe. You see the burette at the left-hand side and the absorption pipe at the right-hand side of the screen. The Hampfel burette is fitted with three-way tap. You can see one. Let me show you. Three-way tap. You see, here is the stopcock, this one. You see, it's two-way. Sometimes sometimes another one is put around this area as well. But this is a two-way cock. Measuring tube. This is the measuring tube. Your burette is the measuring tube. This is your measuring tube. And the leveling tube are connected by rubber. You see, this is the leveling tube. The leveling tube is also called what is it called? Balancing tube. The leveling tube is also known as the balancing tube. And this is the rubber tube. It is about 3 feet. This rubber tube is about 3 feet. It's connected to the measuring tube. And this is the Hampfel absorption pipette. This is the rubber tube, and this is the capillary tube. Now, by looking at the diagram, now let's see their purpose and their function. Now, the gas burette is used to measure the volume of gas collected during an experiment. It has graduated markings that allow for precise measurement of the gas volumes. Now, the function is that the gas collects in the burette, and its volume can be read directly from the scale. The balancing tube, as I said earlier, or the leveling tube, is used to equalize the pressure between the gas burette and the atmosphere. By adjusting the height of the balancing tube, you can make sure that the gas pressure inside the burette matches the atmospheric pressure, which is essential for accurate volume measurement. The stopcocks control the flow of gas into or out of the burette. They can be opened or closed to allow the gas to enter the burette from a gas generating reaction or to release gas. Controlling the flow of gas is crucial for precise measurement because it ensures that only the desired amount of gas is collected and measured. The gas source is connected to the burette through the tubing. The connection allows the gas produced in a reaction to flow into the burette, and the tubing should be secure and airtight to prevent gas leak. Now, here is the setup. Now, in a gas burette, the stopcock is given at the top upper side of the burette. As you can see here, this is the stopcock. The tube of the burette is filled with fluid such as water, mercury, or other kinds of liquid, and is attached to the reservoir of fluid at the bottom of the tube. The top tap is opened. The stream of gas from the supply is passed through. The measuring tube for about 2 minutes is passed through the measuring tube for about 2 minutes. Both the taps are closed. The top of the measuring tube is connected to the absorption pipette. You see, this is your absorption pipette. This is your absorption pipette. Now, via bent capillary and tube and rubber tube, that means this rubber tubing is connected to this. From here is connected to this. So the gas is collected by displacing the fluid from the burette, and the volume of the gas is measured by the volume of the displaced fluid. Let's start with the assay of carbon dioxide, a common gas that needs to be measured in many applications. Now, in various industries and laboratories, it's crucial to know how pure the carbon dioxide is. This is often done using gasometric assays. For carbon dioxide, we need to ensure that the sample is at least 99.5% pure. We do this by absorbing the carbon dioxide in a solution of potassium hydroxide, which reacts with the carbon dioxide. The all reacted gas left behind and is then measured using the Hampel apparatus. This process allows us to determine how much carbon dioxide was present in the original sample. This method is crucial in industries where carbon dioxide purity is critical, such as in beverage carbonation or environmental monitoring. Now let's go through the procedure step by step. First, we use a handheld apparatus with three-way or two-way tap. The three-way or two-way tap is turned so as to connect the measuring tube to the gas air through this side. The top tap is also opened. A stream of gas is supplied to stream of gas from the supply is passed through for about 2 minutes. The tap are then closed. The top of the measuring tube, remember this is your measuring tube, is connected to the absorption pipette. This is your absorption pipette via the capillary tube under the rubber tubing. This is your rubber tube. This is your capillary tube, bent capillary. The lower bulb of the pipette is filled with 50% weight per volume solution of potassium hydroxide. This is filled with 50% potassium hydroxide. The upper bulb is partly filled. When this is filled, this one is filled to the half. The connection is made in such a way that the connecting tube becomes completely filled with the liquid. The top tap of the burette is opened. This tap is opened. The leveling tube is filled with water. This is your leveling tube. It is filled with water. And then is raised so as to drive the whole gas. And the pressure here of the water from the leveling tube will force the gas into the absorption pipette so that it will react with potassium hydroxide. Gently rocking the pipette is carried out 2 to 3 minutes. You rock the pipette for 2 to 3 minutes. It ensures complete absorption of carbon dioxide. Then the leveling tube is lowered. This is your leveling tube. It is then lowered. The small volume of residual gas is drawn back into the burette. The tap is then turned off so as soon as the capillary has become filled with liquid. The levels in the two burettes are adjusted and the volume of unabsorbed gas is read. Each step needs to be performed carefully to ensure that no gas escape and that our measurement is accurate. Each step needs to be performed carefully to ensure that no gas escape and that our measurement is accurate. Accuracy is key to in this process to get a reliable result. Ensuring that no gas escapes when handling the burette. The precise measurement gives us the purity of the carbon dioxide in the sample. Now let's look at the assays of oxygen, another important gas just like carbon dioxide. The purity of oxygen is important in many applications, from medical uses to industrial processes. Oxygen must be at least 99.0% pure for many use, such as in medical and industrial settings. To measure oxygen, we use a reagent called ammoniacal copper solution, which selectively absorbs oxygen. It's a selective process, so it only absorbs oxygen and leaves other gases behind. The apparatus used for this is entirely either a Hamfel or Frankel burette, similar to the one used for the carbon dioxide, but adapted for oxygen. The process ensures that we can accurately measure the amount of oxygen in a sample. The unabsorbed gas is measured to assess the oxygen content. This assay is particularly important in fields like medicine and industrial applications where oxygen purity is vital. Now, let's dive into the procedure for the oxygen assay. We begin by ensuring the burette is completely dry because moisture can affect the accuracy of the measurement. We then fill the burette with the gas sample and add the ammoniaca solution to absorb the oxygen. The ammoniaca copper solution forms a complex with oxygen, effectively removing it from the gas mixture. The volume of the residual gas give us a measure of the oxygen content. Each step must be done with precision, just like in carbon dioxide assay, to ensure accurate result. Frankel burette offers fast result, making it preferable for rapid assays. Now, just like the carbon dioxide assay, the oxygen assay as well, oxygen assay, first the burette has to be dried. The dried burette is filled with gas by passing a stream through for also 2 minutes. Then the tap is closed, just like the explanation before. The plug is removed, then the receiver is filled with ammoniaca copper solution or pyrogalon. The alkaline is an alkaline. The plug is removed and the tap is closed. The central tap by central, the tap solution is allowed to flow into the burette. And the burette is gently shaken to ensure the complete absorption of oxygen, just like how the rocking of the pipette is done. The burette is then inverted. The central tap is then opened. All absorbent is flowed back into the receiver. The central tap is then closed. The burette is turned right way up again, which is then lowered into a cylinder of water. The bottom tap is open. Water is adjusted to the same level inside and outside the burette. The volume of unabsorbed gas is read on the scale. It's just similar, just different apparatus. Factors affecting gasometric assay. We are going to look at temperature, pressure, and predominantly the vapor tension, that is the moisture. There are other factors which include gas purity and reactivity, the time measurement, and the accuracy of the equipment. So talking about the temperature, for us to correct the volume of the gas, we have to correct the temperature, pressure, and the moisture. Now we know that from our Charles law that volume of a gas changes directly with temperature. That is, the volume of gas is directly proportional to temperature. Now, if the gas increases, if the temperature increases, the gas volume expands. Then if the temperature decreases, the gas contracts, reducing the volume. The gas volume are usually corrected to standard temperature, that is 0 degrees Celsius, to ensure accuracy. Now, if you remember your Boyle's law, which says gas volume is inversely proportional to pressure. Now, the lower atmospheric pressure results in gas expansion, while higher atmospheric pressure of the gas compresses the gas. The standard pressure is 760 millimeter mercury or 1 atmospheric pressure, which is used to make the correction. Now, talking about the moisture, the water content. If the gas is collected over water, the presence of water vapor adds pressure. This must be corrected by subtracting the vapor pressure of water, which depends on the temperature, from the atmospheric pressure to the true pressure exerted by the gas. From these, there is an equation that is use to correct to get the actual volume of a gas. The accuracy of equipment you need to calibrate. Calibration of the gas burette, pipette, and other measuring materials are critical. Any errors in this measurement will affect the volume reading and the overall accuracy of the AC. Then the purity of the gas. If impurities in the gas can affect the accuracy of AC. Reactive gases like oxygen, carbon dioxide may also interact with moisture or chemicals in the apparatus, altering the measuring of the volume. You remember we are to measure the volume. We are concentrating on measuring the gasometric assay is concentrated on measuring the volume of a gas. Time measurement also. The time taken to conduct the assay can influence the gas volume, especially if there are changes in environmental conditions like temperature, pressure during the experiment. Now, if we can account for all these factors, we can correctly measure the volume of a gas. Measuring gases accurately isn't just about chemical reaction. It's also about the condition under which we measure them. Like I said earlier, factors like temperature, pressure, and moisture can significantly affect the gas volume. Gases expand and contract depending on temperature and pressure. For instance, let's take for instance, a gas expands on a hot day, just like a balloon might. We have to account for these variables to get an accurate measurement. These slides highlight the importance of, and the previous slides also highlights the importance of controlling these factors during a gasometric assay. The presence of water vapor can interfere with accurate measurements, so it's often necessary to dry gases before measuring them. Because temperature and pressure can vary, we need to correct the gas volume. As I said earlier, we measure to standard condition, usually 0 degrees Celsius and 1 atmospheric pressure. Now, the formula we use for these corrections, I will walk you through how the calculations are done, using the temperature and pressure at the time of the assay to find the corrected gas volume. This ensures that our results are consistent and comparable across different conditions. Now, pressure correction. Why correct the pressure? The volume of gas, as I said earlier, is inversely proportional to its pressure as per Boyle's law. If you conduct an experiment at a different pressure than standard atmospheric pressure, the gas volume needs to be adjusted to reflect this. The formula for pressure corrections, where measured volume is the volume of the gas measured during the experiment. The actual pressure is the atmospheric pressure at the time of the experiment, which is measured in millimeter mercury or atmospheric pressure. This correction accounts for the fact that gas expands at lower pressure and contracts at higher pressure, as you can see in the formula above. Now, the temperature. Now, for instance, if you measure 100 ml of gas at 750 nanometer mercury, the corrected volume is, you see, that is the corrected volume will be the measured volume times actual pressure, that is the pressure you use in correcting, over 760. This is 100 ml is the measured volume, then the 750 nanometer mercury is the actual pressure, then divide by the standard pressure. You get your actual volume when you correct the pressure. Then the temperature correction. Why do you correct the temperature? The volume of a gas is directly proportional to its absolute temperature, measured in Kelvin, following the Charles law. To compare gas volumes measured at different temperature, you need to correct them to a standard temperature, typically 0 degrees Celsius, or we say 273 Kelvin. The formula for the temperature corrections, where 273 Kelvin is the standard temperature, that is 0 degrees. Measured temperature is the temperature of the gas during measurement converted to Kelvin. That is, you are to convert it to Kelvin, you add 273 Kelvin to the Celsius value you got. Now, for example, as in the formula here under the correction for temperature. Now, if gas volume is 100 ml at 250 Celsius, the corrected volume at 0 Celsius, that is 273 Kelvin, is 100 following the times 273 divided by temperature in Kelvin. The temperature you got 25 degrees Celsius plus 273. You get the correct volume, corrected volume of when after you correct the temperature. Now, when you are to correct the tension, the moisture, when a gas is measured in wet state, when it contains water vapor, the vapor exerts its own pressure volume. So pressure on the gas. This pressure needs to be subtracted from the atmospheric pressure before it artificially inflates the gas volume. The gas tension reference, the vapor pressure of water varies with temperature. For example, at 15 degrees Celsius, the vapor tension of water is 12.7 millimeter mercury. At 25 degrees Celsius, it is 23.8 millimeter mercury. This is constant. There is a table in the next slide that shows the temperature, the vapor tension with each temperature, at each temperature. The formula for moisture correction, you subtract the vapor pressure of the water from the barometer. That is, the corrected pressure will be barometric pressure minus the vapor pressure. Now use this corrected pressure in the pressure correction formula. Example, if the barometric pressure is 750 nanometer mercury and the vapor pressure is 15 degrees Celsius, is 12.7 millimeter mercury. The effective pressure becomes 750 minus 12.7 equals to 737.3. Just a brief calculation. So you see here, the tension will not be given, but you can use the temperature to get your vapor pressure. From the next slide, you see the table. Now here, as you can see, at 0 degrees temperature, the vapor tension is 4.6 millimeter mercury. The barometric tension is in the barometer reading in your gasometric AC. That is where you get it. And you use this table like this. This is a standard table. You use it to correct your moisture, vapor moisture. Now, combining all the corrections to account temperature, for temperature, pressure, and moisture, the corrected volume, you see, this is the formula. Measured volume times, that is from your experiment, times 273 Kelvin divided by temperature in Celsius plus 273 Kelvin times actual pressure minus vapor tension pressure over 760. When you combine the whole three corrections of temperature, pressure, and moisture, you get this equation. So this is what you use after you finish calculating, getting from your assay the volume you got, the measured volume you got. You have to correct it using this formula. Now, there is an important consideration. Now, these factors can affect the gas volume, so corrections are very needed, as I said, to ensure the measured volume represents standard condition. Vapor tension, if the gas is collected over water, as I said, the vapor pressure of water needs to be accounted for. The measured volume is the starting point in any gasometric assay before corrections for temperature, pressure, and vapor tension are applied to standardize the result. Now, by applying corrections for temperature, pressure, and vapor tension, you ensure the gas volume measured during the experiment are standardized. This allows for more accurate comparison and consistent results, especially when working with gases under different environmental conditions. Finally, let's talk about oxygen and its compound. Oxygen is usually obtained through process like fractional distillation of liquid air, or electrolysis of water. Once we have oxygen, it's important to test its purity and to check for other substances such as carbon dioxide or any oxidizing agent. Now, the apparatus used for this test like the Hampel apparatus, which as seen in the previous assays. This assay ensure that oxygen we use meets the required standard. In conclusion, gasometric assay are indispensable tools in analytical chemistry, providing us with the means to accurately measure the concentration of gases like carbon dioxide and oxygen. These assays are crucial in many industries, from environmental science to pharmaceuticals. Mastering these techniques will not only enhance your practical skills, but also deepen your understanding of how gases behave in chemical reaction. Now, let's talk about sodium nitrate and mercuric acetate titration. We will be exploring this important analytical technique used in chemistry, particularly focusing on their application in various fields like pharmaceuticals, water quality testing, and more. Titration is a fundamental technique in quantitative analysis that helps us determine the concentration of a substance in a solution. There are different types of titration, such as each serving specific purposes depending on the nature of the reaction. For example, acid-base titration are used to find out the concentration of acidic or basic substances, while redox titration involve oxidation reduction reaction. Precipitation and compleximetric titration are also commonly used for specific types of analysis. Sodium nitrate titration, also known as diazotitration, diazotization titration, is primarily used to determine the concentration of primary aromatic amines. This is especially useful in pharmaceutical analysis. This is based on the principle that primary amines, aromatic amines of the sample, and the sodium nitrate react together in an acidic medium to yield a diazonium salt. The endpoint is marked by the formation of a blue color with starch iodide paper, which is prepared by dipping the filter paper in the starch mucilage and potassium iodide solution. We detect the endpoint of this titration by observing a blue color on starch paper, which indicates the presence of excess nitrous acid. The chemical reaction involved in this titration is straightforward. Aniline reacts with sodium nitrate in the presence of hydrochloric acid to form a diazonium chloride. The titration procedure involves cooling the sample at 15 degrees Celsius, adding sodium nitrate solution gradually and using starch iodide paper to detect the endpoint. It's also essential to prepare a 0.1 molar sodium nitrate solution and standardize it before use to ensure accuracy. Now, you dissolve sulfanilamide, then you cool it to 15 degrees Celsius. You titrate with sodium nitrate solution. As I said earlier, you prepare sodium nitrate solution, 0.1 molar sodium nitrate solution. You take 7.5 grams of sodium nitrate and dissolve it in distilled water. After dissolution, the volume is made up to 1 liter using distilled water. That is how you standardize, that is how you prepare the sodium nitrate solution. Now to standardize standardize it with sulfanilamide, you weigh 0.5 gram of sulfanilamide, that is your primary aromatic amines, and transfer it into beaker where you add 20 ml of HCl and 50 ml of distilled water. You stir and cool to 15 degrees Celsius. Now 20 gram of crushed ice is then added and titrated with sodium nitrite solution. The endpoint is determined with the help of starch iodide paper, which is that a glass rod is dipped in a solution and touched to starch iodide paper. Deep blue color indicates the endpoint. This is used in determination of primary aromatic amines and used for determination of sulfur group like sulfanilamide and the remaining procaine, hydrochloride, etc. In mercuric acetate titration, we determine the concentration of chloride ions by titrating them with mercuric acetate. The reaction leads to the formation of a mercurious chloride precipitate, which we use to identify the endpoint. This technique is particularly useful in water quality testing, industrial applications, and pharmaceutical analysis. The endpoint can be detected visually by using an indicator like diphenyl carbazone, which changes color when the reaction is complete. When performing titration, there are few practical tips to keep in mind. First, make sure all your glasswares and reagents are clean and properly calibrated to avoid errors. During the titration, add the titrant slowly while stirring the solution consistently to prevent overshooting the endpoint. Also maintain the correct temperature and avoid contamination to ensure the accuracy and reliability of your result. In conclusion, both sodium nitrate and mercuric acetate titration are essential techniques used in analytical chemistry. They provide accurate and reliable means of analyzing various compounds, particularly in chemical, environmental, and pharmaceutical fields. Understanding these techniques and applying them correctly is crucial for achieving precise analytical results. Now, some of the brain teasers, I hope you understand what we did from the beginning of the slide. Now, if I'm to ask you, can you explain the procedure? Can you tell me, walk me through the carbon dioxide assay? How do you do it? Tell me the procedure, the step-by-step procedure of carbon dioxide and oxygen assay. If I ask you, what will you say? They are almost similar, but little difference. And the apparatus also for fast result, you can still use the same apparatus for oxygen assay, while carbon dioxide, for carbon dioxide and oxygen assay, why you can decide to change and use the faster method for the oxygen assay, faster apparatus for the oxygen assay. Now, how do you correct temperature and pressure? How do you correct the temperature and pressure of the gas to get the actual gas volume? If I ask you that, why is it affect? Why does the temperature and the pressure affect the gas volume during a gasometric assay? Don't forget your Boyle's law and your Charles law. You explain. Now, the correction. What correction needs to be applied? How can you account for them? Your sodium nitrate titration. How do you determine the concentration of primary aromatic amines? What is the role of hydrochloric acid in this reaction? Your mercuric acetate. How do you perform the titration of mercuric acetate titration? What is the use? What are the applications of sodium nitrate titration? What are the applications of mercuric acetate titration? Hope you can understand. If you understand the explanation, I believe you can answer all these questions. Don't forget, subscribe, like. Don't forget to subscribe and like.